So my name is Trisha Andrew. I'm a professor of chemistry and chemical engineering at UMass, but here today as the founder and CTO of Soliyarn, which is a company that we spun out of work done in my lab at UMass Amherst. And specifically, I'm going to talk to you today about our proposal to make electrically conductive wetsuits for deep sea divers. So let me explain the need first before I explain what our company does and why we're very uniquely positioned to address this. Deep sea diving is actually still pretty much suspended in the 1930s in terms of technology and garments that are used for divers, both from the military and also folks who just like to dive. The kind of environment that you're entering are ambient water temperatures of 20 to 35 degrees Fahrenheit. The problem is that seawater dissipates your body heat much faster than air because water has a much higher thermal transport coefficient. And in addition to that, you're really undergoing very, very high pressure conditions when you're diving underwater. And all of these together complicate not only the kind of electronics and circuitry that you can put on a person, but it really requires you to be heated in order to perform. We are kind of at the limit of human performance ability at these kinds of temperatures and pressures. And the garment that's used the most for deep sea diving is called a wetsuit. And this garment is special among other kinds of fabrics and garments that we're used to in that it actually uses a steady water layer that's right against your skin in order to perform. There are analogs that are called dry suits that actually completely keep water away from your skin, but those dry suits end up being a lot more rigid and uncomfortable to work with. And a lot of active duty personnel who actually have to serve in these conditions and divers themselves prefer wetsuits. Now, the problem with these wetsuits is that they are exposed to salt water, and you really can't put a lot of electronics and metals in salt water and expect them to perform without corroding very, very quickly. So this is where Soliyarn comes in. This company, spun out of my lab again, is an expert in integrating polymer coatings onto fabrics in particular using a technique called chemical vapor deposition, or CVD. CVD is used to make semiconductors reliably since the 1970s. It is a commercial, very, very mature technology. The novelty that our company has expertise in is actually applying those techniques to polymers and all specifically focusing on fabrics. The coatings that we have developed are shown kind of on the right, and I'm highlighting the chemical structure of the coating in particular that's relevant to this project. That's called PDOT chloride. And the important thing is that it's actually what's called a mixed ion electron conductor. It both conducts charges and electrons, but also ions, or chloride ions in particular. And that's the same kind of ion that you'll find in salt water. We also make hydrophobic coatings for waterproofing, and also hydrophobic coatings in particular that allow oil to bead up in addition to water to actually prevent your clothing from getting dirty over time. Our process, roughly summarized, is as follows. You select a substrate of fabric with a particular weight of porosity and a hand feel that your client or the project requires. Simply place it in a reactor, do the coating, do the chemical vapor deposition based on monomers and an oxidant that we select based on our technology, based on our expertise from our employees, and simply either bake it, depending on the kind of coating you're doing, or just pull it out of the reactor. You have your coating pre-made. There are no solvents used in this. There are no emulsifiers, no surfactants, or adhesion promoters. The polymer is actually synthesized and deposited inside the reactor, a schematic of which is shown on the right, directly onto the substrate. It is also covalently grafted onto the surface, which means that we get a lot of laundering stability, ironing stability, mechanical abrasion stability. We have looked at, we have graded these at about 150 wash cycles with detergent, about 40 wash cycles in an industrial machine, 150 in commercial or household laundering machines. Our team is comprised 50-50 of business leaders and science and technical leaders, which allows our company to be really nice, forward-thinking, and we work with current textile mills in the Massachusetts area, largely through efforts from our CEO, AJ, and our COO, Shayanthani, who actually has experience in the textiles manufacturing industry. With our engineers, we basically work with a couple of Massachusetts mills to use old, now defunct roll-to-roll processing steel machines to basically retrofit them with our CVD technology in order to update this very age-old process with this chemical vapor deposition approach that we actually use. The active heating suite that our company has already developed has focused a lot on dry heating applications to date. And I'll quickly go over this. On the right, you'll see a very high-level summary, pictorial summary of actually how we make our active heating elements. We start with cotton as our base substrate because it's very lightweight. It's a natural fiber. It's actually grown. A lot of cotton can be grown domestically. We apply our functional polymer PDOT chloride coating on there. That's the blue circle that you see. That cotton is then cut down into pieces and then sewn into an insert that you see in the middle sector there. That is for a glove. Those cut and sew processes are incredibly modular, can be scaled up to any size and any garment that you see. We have made arm warmers and insoles so far. The inserts are also protected with our patented hydrophobic coating, and you can see the water droplets beating off of it, thus protecting all of the electronic circuitry that goes into that insert. Those inserts finally go into gloves that we work with glove manufacturers in Vermont and also in Iowa and I believe Virginia Beach to integrate these liners into their various different kinds of products. And so we are garment agnostic eventually. And you can see one of our Gen 1 gloves being worn by a retired Navy SEAL, Ryan Angold, who loves them a lot. This is a summary of our suite of technologies. And on the left, you can see a video of our gloves being heated up in real time, just to give you an idea of the time frame it takes to heat things up. They can go up to 160 Fahrenheit in the interest of time. This movie is only showing the heating going up to 110 Fahrenheit. We could reach 110 degrees in about 2 minutes, 160 in less than about 8 minutes. We've also, as I said, made arm warmers and heated insoles that allow us to insert these heated elements, these cotton-based heated elements into different kinds of garments. And our heated glove very recently was selected as Soldier Systems' industry favorite product of a trade show just last month. For this project call, what we are proposing to do is to translate our technology into these wetsuits that I mentioned before. Now, the key that allows us to basically make this kind of prototype is, once again, our active element, PDOT chloride, a conjugated polymer, which is a mixed electron ion conductor. And what that allows us to do is find many different kinds of approaches to insert these heating elements into the wetsuit. Firstly, we could simply take the inserts that we've made for our gloves, arm warmers, and heated soles and stitch them into a wetsuit. As the insert I showed you is hydrophobic, and so that should actually protect the elements inside and allow the circuitry to still do active heating via joule heating without losing efficacy and without corroding. The other alternative is to directly coat neoprene wetsuits. Another big issue with wetsuits is actually the supply chain. Neoprene is exclusively made in Japan, and the neoprene is then bonded to fabrics in the United States to make a completely domestic supply chain, especially for the military. So we could also just coat our wetsuits directly, coat the polyester fabric that's bonded to the neoprene directly, and perform active heating. And in fact, we've shown that we could do that, not only coat the heated wetsuit, the polyester backing, of the heated wetsuit, but we could also show that it does electrothermal heating when you pass 6 volts through it, 6 or 8 volts, I apologize, don't remember. And so for the rest of this project, what we're going to do is effectively elaborate this art, articulate the circuitry that goes into the wetsuit, and confirm that these kinds of heating elements retain their electrothermal performance under high pressure while also being exposed to salt water. I believe that's the end. So I think I should be right on time. So once again, thank you for sticking with me through all of the technical difficulties. My colleague Timothy Monroe and I will be at our booth if you have any questions, or if you want to see these videos again, we'd be happy to play them once more for you. Thank you.